So now we go to the deformation spaces of XG structure on orbifold. So we'll first give you the definition and the local homeomorphism theorem, the isotopy lemma, and the outline too. So this is sometimes called the Ehresmann-Thurston principle. So I think the Ehresmann first did this. Uh, okay, so these are the references you should look at and for which and also books. So first, we want to define the deformation space. So this is a generalization of the Teichmüller space. So you consider all the XG structures on an orbifold M. Okay. So, but this is too big actually. So how do you say we want to see the trivial equivalence? So two are equivalent if there's some isotopy such that phi star mu one. So given any structure, you can shift by any isotopy. The charge will still be the charge and so on. Okay, so these are really trivially equivalent one. So you want to quotient by these isotopies. Okay, and now we can reinterpret this space so that in the Teichmüller space case they do the same thing. So we take a look at all the set of diffeomorphisms from M to M prime. So M is fixed, and then M prime is any sort of axis orbifold. So this is done for convenience to think. Okay, and then if you have any two of them, they will be considered equivalent if the axis diffeomorphism, if there is a axis diffeomorphism from M prime to M tilde prime, so that H circle F is isotopic to Z. Okay, so if you can isotopy F to Z here. Okay, so then the quotient space is same as this one because you can think of this second M as some M prime, and then these isotopies, the isotopy, and any M prime actually you can push it back to M and make it M by this because they are actually diffeomorphic anyway. So these are really just the way to push out the definition of this to just some more manageable looking thing. Okay. So that's what you do in Teichmüller space case as well. Okay. And so now we do another interpretation. So it identify pi1 of M with pi1 of M times I. So that's the same group, even if M is a orbifold. And we consider the set of diffeomorphisms F to M tilde to M prime tilde. So you just take the universal covers, which is equivalent respect to some F star for next G orbifold M prime. And then we take the equivalence relation. So we have this F and G. We say there's equivalent if you can find XG map here so that phi circle F is isotopic to G. By some isotopy, which is equivariant respect to these homomorphisms. Sorry, I did use same letters here, but I mean, so this, right. So I'm using the right writer. So this diffeomorphism is always going to be equivariant respect to this homomorphism, and the point is that these are equivariant respect to these both, which has to equal. Okay. Okay, and then these isotopies also has to be equivariant. Okay, right. So then we denote this set by TIM, and of course this set is exactly the same as the one before, right? Because I'm just what I did was just lift to the cover and then stated the same theorem. Okay, by equivariance. Okay, so that's no surprise there, and then now we define SM. So this is a little bit bigger space than this. Okay, so how do you do that? You take a set T F tilde going prime tilde then prime here. This is a diffeomorphism orbifold, and D is a diffeomorphism equivalent respect to homomorphism. Yeah, that's wrong. This is actually just the developing map. Sorry, that's completely wrong. So I will correct that. Yeah. So if two are equivalent if there is a diffeomorphism from M to M prime to M double prime, so that this D prime circle P tilde is D, and there is an isotopy like this, which is equivalent with respect to this. Okay, so this developing map is of course determines XG structure. So in the previous one, you had if there was a XG map, then that's what we required. But here I'm just saying that this is same this development map is same up to this diffeomorphism. Okay, so that's all I'm saying. Okay, so that's a little bit sharper definition, and then we can give a topology on this space by the CR topology using U D circle tilde. So whenever we have these, then of course if these D circle F tilde are the same, then of course you just identify them. And then CR topology is just given by given this is just a map defined on M tilde. So there's a compact open topology, and the CR topology means that you use the basis, which is you use a CR norm on the every compact set. Okay, so that's the definition of this topology. Okay, so it has a relation to compact open topology. So this space is a little bit different because I required this one. Okay, but then there is a natural action of G here, which is just that you act by circle G here. Okay. Okay, so that's the only difference. And then the quotient space is the deformation space. It's the same as the deformation space. I mean that it's one-to-one equivalent to this, because we showed that DIM is one-to-one equivalent to this space. So given an element here, there's a developing map equivalent to respect to this. So suppose I have an element here, okay, DIM, and then these are equivalent. So there's an XG diffeomorphism like this, and the global charts for both of these differ by only element of G. So you get this D, but they if they are equivalent in this DI space, they are differ by element of G. So you get for each element here, you get an element here up to G. Okay, so you get a one-to-one element here. So conversely, if I have an element here, then you obviously obtain a XG structure, right? Because you can pull back using the developing map. And if they are equivalent, then there's a diffeomorphism, so that this is going to be D prime G circle D, and this means that this is a XG diffeomorphism. So if they are equivalent up to this action of G, then there has to be this G. Okay, so this means this is XG diffeomorphism. Okay, so therefore I showed that this is one-to-one equivalent to this. Okay, so this is just the quotient space of the SMG. So this is a right action. I mean the left action here, right? And actually, you can think of isotopy as a right action. So it acts in on the left and then right. Okay. So that's the definition using these 3 point of view. And then so now we want to do local homeomorphism theory. So so let's look at the representation space. Suppose we want to consider pi to be finally presented. So that's what we want to do usually. And then if M is a compact N orbifold, so this is true. So we take G1 to GM set of generators and R1 to RM the set of relations. And the set of homomorphisms can be identified with subset of Gn of M. Okay, by you send each homomorphism to the element of these images of the generators, and then this is clearly injective map, because if you have a different image for a different generator, then of course it's a different different homomorphism. So, and then if you have any different homomorphism, then of course it will have to differ in the generators, right? And then, of course, this image can be described as algebraic subset defined by these relations. So these will satisfy some relations because each of these relations here will give you relations here. Okay, and then if you satisfy these relations, then that will also give you element of Gn will give you the homomorphism because it satisfies these relations. Okay, so that's another easy thing to see. So if the relations are satisfied, then we can obtain the representation. So we denote this space by hom by G, and we can think of this as a subset of Gn. Okay, so there's some algebraic subset. And then there's action here by conjugation because I mean usually these inner automorphisms are considered the trivial ones. So you have to kind of give this action and then you consider these to be the same ones. So you call this representation space as the quotient space of this. So at the moment we're just looking at the set theoretic quotient without any topology here. So in the algebraic geometry, of course, you want to make this into variety, and then therefore they do something like GIT quotient, but we don't do that here at the moment, and we're just using the set theoretic quotient space. So of course, this has a right as a subset. It has a topology, point set topology here, and then you just take the quotient topology here as well. So that's what we do. So then the problem is this is no longer Hausdorff. Okay, subtension is not Hausdorff. So that's the problem. Okay. And the whole map is given by this SM going to the home pi 1G. So SM mod G is the deformation space, right? So and the home mod G is the representation space. Okay. So these are both right actions. So what we do is the Lip's map. Okay. So depth of that. So we get SM going to home G. So then this is actually a local homeomorphism when M is a closed orbifold. Okay. So the basically you send this the F tilde to the associated homomorphism. So for each element you get a homomorphism. So that's why. Whole is continuous. You can see that because if D prime F D circle prime F prime is sufficiently close to this on some large complex set. So that's just the CR topology. Then, of course, the holonomy of the generators are very close. So because these charts are very close, this means that whenever you do the deck transformation, that has to be very close as well. So they differ by cross by elements. Okay, so these homomorphisms. So that's how you prove the continuity. And the local homeomorphism theory is very important, and it's first done by Bayer, and so the same can be done for before, but we're not really doing it here. Okay, and then of course Thurston gave a proof of like this, but I guess John Morgan later gave a lecture on it, which written up by Locke in his thesis, and Canary and Epstein gave a proof of this. So they have this paper. They deal with all the manifold, including the ones with the many boundary, but okay, so but they have some different things here, like our topology, so on. Okay, so the fact that this is a local homeomorphism is a very important thing, and but what we want to do is actually we want to look at the stable subset of home where GX properly. So we note this space by home as I and its quotient by left as by G. So here the action is proper, and the quotient space is a nice space which is not which is Hausdorff, so on. So it could be better than Hausdorff, but we want to just stick with that. And then by DSM, the subset of this deformation space. So I switch notation, but I guess this is a deformation space, which holonomy is stable. So you can show that this is actually open set. Okay, and then of course this is an open set here. And so then there is a local homeomorphism. It's open set when this is nice, not always, but I mean you need some conditions. Okay, and pi is general enough. Okay, then there is a local homeomorphism like this. So since the right actually the development is conjugation and Holm, so you get an induced map like this. Okay, so this is a local homeomorphism. Okay, okay. Right. So that's an important theorem, but of course, in general, when you're just looking at D and then go to rep, then this is only open map. Okay, so that's what people usually will say without knowing too much details. Okay, so uh, the basically I want to give a proof of this, but just a skimpy proof. So if you just have any finite group GX going to X. Then there is a neighborhood, which is a cone over semi-algebraic set. So you think of these as a semi-algebraic set, then you can, so any point has a neighborhood, which is a cone. Okay, so cone means that something semi-algebraic set times R, but you identify one side to be just one point. Okay, then the GX is a stabilizer group of any or finitely presented group. Okay, and then what you do is you have any compact subset F of an open ball, then GB acts on F and B, and then SB some cone neighborhood here. Okay, and then so if you have any map which is GB equivariant, iso then the isotopy for every H, um, then you can actually extend to the open set. So this is a extension of what's called a sub-isotopy lemma. So that's a very difficult theorem, but maybe but it's quite old theorem. But you can just extend this to a finite group action, and usually using the vector field theory. And uh, and then once you have this local result, then the theorem is just that you give a Riemannian matrix so the singularities are totally geodesic, and you cover it by finite group cover, which is by a compact convex neighborhood, which is inside the convex open neighborhood. So these are all convex with respect to the Riemannian metric. And then you look at the intersections of largest number of such sets. So there's so these are locally finite covers. So you choose locally finite cover, and then you look at the ones which is the largest number of intersections. And then you deform these ones first using the element of G, and then you can then keep extending using these sub theory. And then you go to the next level ones and so on, and then you do the induction. So that's basically the idea of Thurston, but I wrote it in detail in my paper, so you should look at that one if you want to know the details here. Okay, so that's the end of this lecture, sir. Okay.